Welcome back to chapter 19. We ended with some problems last time, some questions, and I want to talk a little bit about modeling problems, like some other types of questions that you could be asked. For instance, what if you were asked number of particles? Well, number of particles would equal the total charge divided by the magnitude of each charge. So that would be whether it be a positive or a negative. If you remember, you have an electron charge of 1.6 times 10 to the negative 19th coulombs. So if it's an electron, it would be negative. If it's a proton, it would be positive. So we have that charge. So I can figure out the number of particles by taking my total charge divided by that number. So that's one type of question you could be asked. You could be asked what the total charge is. Well, if I know delta V is equal to delta EPE over Q, Q must equal the electrical potential energy divided by delta V. So the charge equals the energy difference divided by the electrical potential difference. And I could always relate EPE to work. So I could also say that the charge is equal to negative work divided by the voltage difference. And another type of question has to do with energy use and power. Now we haven't gotten to watts yet, but power would be the change in electrical potential per unit time. Actually, power would be volts per unit time. But I could, yeah, I'm wondering why it doesn't have that here. I think it's, maybe I got it wrong in my head. Let's just believe that I have it right on the slide. So power is delta EPE over time. Something per unit time is power. So if I know the power and how long that power is applied for, I know what the electrical potential difference or electrical potential energy generated is. So the rate at which power or wattage is used times the amount of time that it is used tells you how much electrical potential difference you could create. So the first two are just kind of conceptually like working through things we already knew. And the last one there is kind of something new, applying power to it. But these are the kind of questions that you're going to want to keep an eye out for. When you, of course, we don't have homework this year, but this was basically, I made this slide basically to help people do these homework questions. But if it's on the slides, it could be on the test. Okay. So let's review. We have energy, and we now have 5 different types of energy. We know that electrical potential energy is equal to charge times the electric field strength times the displacement. We know that work is equal to the change in electric potential energy, and that's true. Work is also equal to the change in gravitational potential energy. So it's just another type of work. And we have voltage difference, which is electrical potential is equal to change in electric potential energy divided by the charge. And we had an electron volt. So these are things that we've discussed so far. Let's go on to new stuff. There's a lot in this chapter, I know. What about the electric potential difference created by 2-point charges? All right, so we have 2-point charges now. We're going to talk about the voltage difference between them. Remember, the magnitude of electrostatic force is given by Coulomb's law, KQQ over R squared. Through integral calculus, I'm skipping some steps, work is equal to KQQ of RA divided by KQQ of RB. So the radius of the distance from how far you are from one object minus how far you are from object B. So you have object A and object B, or point A and point B, I should say. I said object, but I meant point A and point B. So the work that you get going from point A to point B equals KQQ over R minus KQQ over R, going from A to B. Now, knowing that, I can calculate the potential energy, the potential difference as work divided by Q. So it's work divided by Q. But I now know that work is KQQ over R, and that Q naught is now going to cancel out. So I have another way of looking at potential difference. and this is kind of our where we're heading now. I have voltage, which before we saw was delta EP over Q or negative work over Q, can also be, and these are Q naughts here, I should have put that in, the test charge. It can also be determined as K, the constant, times Q divided by R, how far you've moved. So the potential of a point charge V is KQ over R. So it's another way of calculating it. Q is the Coulombic charge, R the distance, and K is a constant. And here it is kind of just graphically explained. I have a charge that's a certain distance from, it moves from RA to RB. Okay, so Q naught is the charge that's moving, and there's a force that it's positive, so it's moving towards a lower potential, and it moves from A to B. And the voltage, the potential of the point charge as it goes from A to B is KQ over R. Let me show an example. Using a zero reference potential at infinity, so basically if this goes all the way down at infinity, it becomes zero. And on the test, just assume that that's the case. I won't write that in. Determine the amount which a point charge of 4 times 10 to the negative 8 coulombs alters the electric potential at a spot 1.2 meters away when the charge is positive and negative. Once again, you know that the one is just going to be the negative of the other. So I have a positive 4 times 10 to the negative 8 coulombs and a negative 4 times 10 to the negative 8 coulombs at 1.2 meters. All right, so that's what we know. So what is, how much does that charge alter the electrical potential at a point 1.2 meters away? Now the answer is kind of already shown in the drawing, but let's work it out, okay? Voltage is equal to K. K is a constant, 8.99 times 10 to the 9th, Newton meter squared per coulomb squared, times the magnitude of the charge, 4 times 10 to the negative 8th, divided by the distance, 1.2 meters. So at 1.2 meters away from this charge, you will have a potential of 300 volts, the electric potential. So KQ over R tells you the potential. So if I was 1.2 meters away, and that's a pretty strong charge, I'm going to have 300 volts. If it's a positive charge. If it's a negative charge, I just replace this positive 4 with a negative 4. And notice how this one does not have an absolute value there. So it kind of gives you the potential difference, the direction in terms of a sign here. But if it's the opposite, it would be negative 300 volts. So this gives you another way, it's just another way of calculating electrical potential difference. And that's what voltage is. What is the difference between potentials? Think about it like gravitational potential. What is your potential to go from point A to point B? Independent of what your mass is, this is what is your potential independent of what your charge is. Okay. Now in all these in this case, there's only one charge. But what if I have two charges? Well, like all things, I just add them together. So let's look at an example where I have two charges. At locations A and B, find the total electric potential. So I have two charges in this system, a positive 8 and a negative 8. Now since the equation is KQ over R and the Q's are equal but opposite signs, I can tell you without even doing it that in the middle, since the charges are the same, in the middle, I'm going to have zero potential because I'm going to have a positive minus the exact same number. But let's figure it out at A, just to show you how that would work. Well, at A, I take the voltage due to one of the charges, which would be K 8.99 times Q divided by the distance of 0.2 meters, and I add the potential from the other one, only now the distance is not 0.2 meters, it would be 0.6 meters. Add those together. The 0.2 is going to have a greater effect. So because I'm closer to the positive 8 coulombic charge. So that would be a 240 volt potential. If I'm in the middle, since they both would be divided by 0.4 and they're both the same voltage, just one's positive, one's negative, or coulombs, just one's positive, one's negative, they're going to cancel and I get 0 volts. So if I'm right in the middle, I have no potential, or the electrical potential is 0. All right. Now what if so there's a 0 point in the middle, but could there be other 0 points? Well, let's look at this example conceptually. I have two charges, but in this case, one of them is twice as strong as the other. So the 0 point won't be right in the middle. If I do the math, the 0 point will be 1/3 of the way from Q, because this distance will be 1/3 and this distance will be 2/3. But if this is the case, and it's 0 right here, wouldn't it also be 0 way out here? So let's say that it's being attracted to Q and repelled, attracted to negative Q and repelled from positive Q. If I'm twice as far from a twice as strong positive Q, so this distance here is twice this distance, but this distance out here, the far right dot, is also twice as far from the plus 2Q as it is from the negative Q. So without even doing any math, I know that there have to be 2 points where the total potential would be 0. Any place where I'm twice as far from the positive 2 as I am from the negative 1. I think that's a good place to start, and I'll come back and I'll talk about equipotential surfaces in the last video for this chapter.